Hello students, let us start our today's session from the chapter Alcohols, Phenols and Ethers. So in this case we are going to see about preparation of phenol and properties of phenol and alcohols. Let us see first of all preparation of phenol. Phenol that can be prepared by four different methods. One from Dow's process, from benzene, from aniline and from cumene. Let us take Dow's process. This process already we have discussed in our haloalkanes and arenes chapter under nucleophilic substitution of chlorobenzene. So here the chlorobenzene does not undergo nucleophilic substitution due to the partial double bond character, sp2 hybridized carbon, repulsion between the nucleophiles and their unstable phenyl carbocation. But the molecule is made to undergo nucleophilic substitution under the vigorous conditions of 623 Kelvin and 300 atmospheric pressure. It is converted into sodium phenoxide where this HCl is being removed. And after that, followed by hydrolysis, we are getting phenol and sodium chloride. Then from benzene. Benzene first of all converted into benzene sulfonic acid by treating with oleum. Oleum is H2S2O7. When sulfur trioxide is passed through sulfuric acid, we will get oleum, such a strong acid compared to sulfuric acid. So this sulfuric acid that combines with one of the hydrogen atom of the benzene is being removed as water molecule and hence we are getting benzene sulfonic acid. This benzene sulfonic acid being acid because of the presence of the hydrogen proton that may react with the base to form the sodium salt of benzene sulfonic acid. Followed by acid hydrolysis, sodium will be removed as NaHSO3, so we will get alcohol. From aniline. Aniline actually it is first of all diazotized to benzene diazonium chloride. Followed by just warming with the water, it forms phenol. This diazotization is possible only under the condition of 0 to 5 degrees Celsius since the diazonium salt is highly unstable at room temperature. So aniline diazotized to form benzene diazonium chloride followed by just warming with the water. The nitrogen gas is expelled out and the chloride is removed as HCl. So we will get phenol. The next method is from cumene. In this method, we can manufacture the phenol for commercial purposes. What is cumene? Cumene is isopropyl benzene or it is 2-phenyl propane. So this isopropyl benzene is prepared by treating benzene with propene in presence of orthophosphoric acid at 570 Kelvin. So here the one of the hydrogen from the benzene ring that adds with the CH2 group of propene. So CH2 with the H that makes CH3 and this position the secondary carbon CH gets attacked. So that's why we are getting 2-phenyl propane. This undergoes air oxidation. Air oxidation means we have to take molecular oxygen. Usually oxidation carried out by nascent oxygen, but here it is undergoing air oxidation. That's why O2 is taken, and it is possible in presence of the weak base sodium carbonate where the CH group is converted into COOH. This is hydroperoxide. It is the COOH. You are finding oxygen single bond linkage. This linkage is said to be peroxide linkage, and this peroxide it has one hydrogen, that's why it is called cumene hydroperoxide. Followed by acid hydrolysis, the bond it gets broken between the peroxide linkage. So this OH group and the 2 electrons of oxygen bond get shared with OH and CO bond, and here also the bond broken. That's why we are getting acetone and phenol. That's all the different methods of preparation of phenol. Now let us see what are the physical properties of alcohols and phenols. Alcohol, their physical state, actually lower members are colorless liquid, and lower members, few of them have some smelling also. But higher members, they usually exist in waxy solids. In its melting point, boiling point. When we discuss about melting point, boiling point, we have to consider their molecular mass and van der Waals forces. When molar mass of the compound increases, van der Waals forces also increases due to the increased structure. Whether it follows that normal linear structure, then van der Waals forces also be increasing. Besides that points of molar mass and van der Waals forces, the alcohol molecule, they have strong associative intermolecular hydrogen bonding. How the hydrogen bond is formed? Hydrogen bond is usually formed between the most electronegative atoms of fluorine, oxygen, nitrogen. Only these 3 elements able to make hydrogen bond with the hydrogen atom. So to form a hydrogen bond, the molecule should have at least either of the atom fluorine, oxygen, nitrogen and hydrogen. So in alcohol, we have oxygen as well as hydrogen as its functional group. So one of the alcohol molecule, it gets bonded with hydrogen. The hydrogen bond usually existing between hydrogen and the most electronegative atom of oxygen. So every oxygen and hydrogen, they get interlocked with hydrogen bonding. So besides van der Waals forces, hydrogen bonding also including, and hence the boiling point of alcohol is very high compared to ethers and hydrocarbons of comparable molar masses. The molar masses of the compounds will be very close to each other. For them, when we compare, alcohol has higher boiling point due to the presence of intermolecular hydrogen bonding. Then solubility. Solubility, alcohol, they have hydrogen bond. Water also possess hydrogen bond because H2O, every oxygen atom will be oxygen as well as hydrogen will be hydrogen bonded with other water molecules. So when alcohol and water, they have similar forces of interaction, say hydrogen bonding, so they do miscible with one another. So for the solubility, the important condition to satisfy is they should have the similar interaction forces. So alcohol has hydrogen bond as well as water has hydrogen bond. When do mix together, the hydrogen bonding present in alcohol gets broken and the hydrogen bond present in water, that to be broken, and a new hydrogen bond is set up between the alcohol and water. So here similar types of forces being broken and the same type of forces once again existing between water and alcohol. So the energy released during the process will be sufficient to make a new hydrogen bond, and hence alcohols are completely miscible with water. But the higher members of alcohol becomes insoluble. This is why the R group, size of the R group increases, they become hydrophobic in nature. So lower members of alcohol, say methanol, ethanol, propanol, butanol, and all soluble in water, but when it goes the number of carbon beyond 5 or 6, that becomes hydrophobic and the solubility gets decreased. Now let us discuss about properties of phenol. Phenol is a highly corrosive substance. If it falls on the skin and all, the skin will be corroded. And it is hygroscopic, that means it can absorb the moisture, and it is a poisonous one. Being colorless, but it turns into pink due to air oxidation. It can undergo spontaneous oxidation with atmospheric air, so the colorless phenol that can turns into pink. Melting point, boiling point also higher, because in phenol also the molecules gets associated with intermolecular hydrogen bonding. And when we discuss about the solubility of phenol in water is very slight, because the benzene ring that becomes hydrophobic, and hence the solubility of phenol in water is sparingly soluble. That's all the physical properties of alcohols and phenols. Chemical properties of alcohols and phenols. Chemical property of alcohols and phenols, they can undergo in two different ways. In alcohol, the reaction may proceed due to the cleavage of oxygen-hydrogen bond, where the hydrogen becomes the leaving group of alcohol. At the same time, when the reaction due to cleavage of COH bond is taken place, where the OH group becomes the leaving group of alcohol. So, in alcohol, whether the hydrogen atom of OH group or the functional group OH itself can be substituted by some other group. So, alcohol can undergo two different reactions in which according to the cleavage of carbon-oxygen bond or oxygen-hydrogen bond. Similarly, in phenol we have a benzene ring with OH group. So, phenol, it may undergo the reaction due to the OH group, also the reaction due to the benzene ring. The benzene ring will undergo electrophilic substitution reaction, and the functional group may undergo the reactions of esterification, reaction with the metals, bases, etc. Let us see first of all the reactions of chemical properties of alcohol, in which we are going to find the cleavage of oxygen-hydrogen bond. Here we may find two reactions that will proceed through the cleavage of oxygen-hydrogen bond. One, the reaction with the metals. Metals are usually highly electropositive. So, when we take the strong electropositive metals like sodium or aluminum, they may displace the hydrogen atom of alcohols, where hydrogen is being displaced. So, sodium, it displaces this hydrogen atom, and hence it is removed as half H2, because 2 into half equal to 1, only one hydrogen is displaced. So, where we are getting, this is a minus group, this is a plus group. So, CH3 CH2O minus with the Na plus, it forms sodium ethoxide. And this sodium ethoxide is a strong base, even more than the alkalis, potassium hydroxide, sodium hydroxide, like that. So, because of its strong base as well as its the bulky size of alkyl group, we are taking this bases for the elimination reactions. And if you take tertiary alcohol, once again the hydrogen atom of tertiary butyl alcohol is replaced by aluminium. So, the name of the compound is aluminium tertiary butoxide. So, here we have aluminium valency 3. So, it combines with the 3 times of butoxide group. So, when you put over here 3, the hydrogen goes only 3H. But we need 3 molecules. So, I can make it as 3H2. So, it becomes 6, and hence the tertiary butyl alcohol is multiplied by 6 times. When it goes 6, it has to be made into 6. So, we are multiplying this is by 2, where aluminium also becomes 2. So, aluminium is balanced with 2. The next one, esterification. Esterification is the process of the treatment of alcohol with the acid that forms ester and water. So, in this process, the hydrogen atom of alcohol is being displaced by the OH group of carboxylic group, and it forms ester. And the reaction takes place in presence of concentrated sulfuric acid in case of carboxylic acid and alcohol, because there is a removal of water from the functional group of carboxylic group and alcohol, and this water that may shift the reaction to the backward. So to drive the equilibrium towards the forward reaction, we are taking concentrated sulfuric acid where it behaves as dehydrating agent. So this may absorb the water produced. So the equilibrium will be shifting only towards the forward direction. So the reaction of alcohol with the carboxylic acid is termed as esterification. The alcohol, not only with the carboxylic acid, it may also react with the derivatives of carboxylic acid, acetyl chloride and acetic anhydride. So in this, the OH is replaced by Cl. Here the OH is replaced by acetate group, CH3COO group. So these are the derivatives of carboxylic acid. When we have acetyl chloride, the leaving substance is HCl. HCl is a strong acid. So this acid produced to be neutralized. That's why in this case we will take base for the reaction, because the presence of base that may neutralize the acid, and hence the reaction will proceed in the forward direction. Similarly, with the acetic anhydride, anhydride means no water. So, two molecules of acetic acid, when it undergoes condensation, a molecule of water will be lost, and hence the product is said to be acetic anhydride. When it is treated with ethanol, once again we may find the formation of this group, CH3COOH is left, and the rest of the product CH3COO, CH2, CH3. So we are getting ethyl acetate. One more information. In this alcohol, we have taken alkyl group. Even this alkyl group even be an aryl group. So aliphatic as well as phenol, they may undergo esterification reaction. Depends on the alcohol and carboxylic acid, the products will be formed. Let us see the next type of reactions in which the cleavage of carbon and OH bond is observed. So let us see the first of all, nucleophilic substitution reaction. This we already have seen in haloalkanes chapter under the preparation of alkyl halides from alcohols. Both of the reaction we discussed over there. Here the phosphorus trihalide or pentahalide or thionyl chloride SOCl2. They may displace the OH group with the corresponding halogen atom. So in this case I have PCl3, there are 3 chlorine atoms, so we are getting 3 CH3 CH2Cl. When it is 3 times, then the ethanol will also be 3 times, so we are having 3 hydrogen, 3 oxygen, and hence we are getting phosphorus acid as the byproduct. Similarly, when you have phosphorus pentachloride, see this hydrogen and chlorine that makes HCl. This oxygen with the PCl3 that makes POCl3. So after the removal of OH, this chlorine that attacks the position, so we are getting ethyl chloride. So with the phosphorus pentachloride, we are having chloroethane, phosphorus oxychloride and hydrogen chloride. In the case of thionyl chloride, this chlorine is replacing the OH group, so we are getting ethyl chloride, and SO with the oxygen that makes sulfur dioxide, and this chlorine with the hydrogen that makes hydrogen chloride. The next reaction with the Lucas reagent. What is Lucas reagent? The concentrated hydrochloric acid with the anhydrous zinc chloride, that mixture is found to be Lucas reagent, and this Lucas reagent is helpful to identify the type of alcohols. We have 3 types of alcohol, depends on the number of alkyl group attached to the functional carbon. It is a primary alcohol, because it has only one alkyl group. This is a secondary alcohol because this CHOH group, it has two alkyl group, and the next one is tertiary alcohol in which we may find the 3OH group. So by this method we can identify what type of alcohols we have depends upon the formation of turbidity. When primary alcohol reacts with the HCl in presence of anhydrous zinc chloride, we didn't find the turbidity formation even for long time. This is why the reaction, it won't take place at room temperature, so no turbidity is formed. But when in the case of secondary alcohol, when it is treated with the Lucas reagent, it forms 2-chloropropane, but the turbidity formation, it takes some time, about 5 to 10 minutes. But tertiary alcohol, as soon as the reagent is added, turbidity will be formed. So there is no time lagging. So when the turbidity immediately forms, we can identify the given alcohol is a tertiary alcohol. If turbidity, it takes time for the formation of turbidity, then you can say it is a secondary alcohol. The primary alcohol at room temperature won't react, but if you heated this mixture, it forms chloroethane. But we are carrying out the reaction at room temperature, so we didn't take the process in presence of heating. Oxidation of alcohols. Alcohols ready to undergo oxidation with mild oxidizing agent as well as with the strong oxidizing agent. The mild oxidizing agents are the chromic acid or chromic oxide and all. So this chromic oxide, when we have taken the primary secondary alcohol, they may oxidize to their corresponding carbonyl compounds. But the tertiary alcohol do not undergo any change with mild oxidizing agent. So here you may observe the primary alcohol that gives aldehyde as the product, but the secondary alcohol gives the ketone as the product. So we have to note, primary alcohol on oxidation always give aldehyde. Secondary alcohol on oxidation always give ketone. Why? This is the site where oxidation takes place. So the oxidation is nothing but a removal of hydrogen. The OH hydrogen and one of the hydrogen from CH2 that gets converted into, that hydrogen gets oxidized to water. So because of the removal of hydrogen and the other hydrogen from carbon, we are getting a double bond between carbon and oxygen. So the double bond should be represented like this. This is the structure of aldehyde. Similarly, when you consider that 2-propanol or the isopropyl alcohol, secondary alcohol, these two hydrogen is being oxidized to water, and hence the removal of hydrogen, that can move like this, and hence that makes a double bond between carbon and oxygen. So secondary alcohol gives ketone, primary alcohol gives aldehyde, but a tertiary alcohol with mild oxidizing agent, no products will be observed. But at the same time, when these alcohols is carried out with strong oxidizing agent, they give rise to the last product of carboxylic acid. So all the alcohols upon oxidation, the final product formed will be a carboxylic acid if at all reaction takes place in presence of strong oxidizing agent. So mild oxidizing agents stop the reaction up to the formation of carbonyl compound, but strong oxidizing agents that can proceed the reaction until the formation of carboxylic acid. So here we have taken once again the primary alcohol, it oxidizes to aldehyde and further it oxidizes into carboxylic acid. And the next one, secondary alcohol, we have the CHOH group. This is oxidized to the ketone. On further oxidation, it is converted into carboxylic acid. So primary alcohol to aldehyde and then to acid. Secondary alcohol, this is to ketone and then to acid. When we find the tertiary alcohol, it requires very high temperature because tertiary alcohol resists for oxidation. But in presence of a strong oxidizing agent and high temperature, we can make this compound to undergo oxidation. But during this, it will give rise to a cleaved product. Cleaved product means none of the product will have same number of carbon as that of tertiary alcohol. That's why we are saying the products obtained are cleaved product. How the oxidation takes place? This is the COH group. Actually, the COH do not oxidize because that carbon has no hydrogen, the functional carbon. So the first oxidation takes place among COH and CH3. So where we are getting first of all ketone. And the CH3, the alkyl group usually oxidizes to formic acid, HCOOH. But that formic acid is highly further oxidized to carbon dioxide and water because of strong oxidizing agent. So we may find 4 carbon in tertiary butyl alcohol. When you go to the product, you may find the product it has 3 carbon. On further oxidation, you may find it has only 2 carbon. So the number of carbon decreases. This is because the oxidation takes place not only in the functional group, that along with the alkyl group it undergoes oxidation. So one of the alkyl group that is oxidized to formic acid further oxidized to carbon dioxide and water. So every cases you can write minus CO2 minus H2O. Here also minus CO2 minus H2O. This is what the cleaved product. But in secondary alcohol, you may find it has 3 carbon in the secondary alcohol. In ketone also you are finding the 3 carbon. But on further oxidation of ketone, you may find it has only 2 carbon. So ketone, it always takes place the oxidation with acyl group, that is the COCH3 gets oxidized. But in primary alcohol, they retain their number of carbon atom from alcohol to carboxylic acid. So this is also we can consider based on their molecular mass empirical formula determination. You can take this method also to identify the type of alcohol. If the molar mass and the empirical formula are and all similar maintained, you can say it is a primary alcohol, or the molar mass is reduced to a considerable value where you can say the compounds are secondary or tertiary alcohols. Catalytic dehydrogenation of alcohols. So here we are going to take all the 3 types of alcohol. When these vapors of alcohol is passed over the heated copper at 573 Kelvin, it undergoes only dehydrogenation. Dehydrogenation, removal of hydrogen. Let us take the primary alcohol, how the removal of hydrogen it proceeds, such a way it goes. So the carbon oxygen that develops a double bond. So when primary alcohol undergoes dehydrogenation, we are getting aldehyde as the product. Secondary alcohol, 2-propanol we have taken, that will also undergoes dehydrogenation among the functional carbon and OH group. We are getting ketone and hydrogen. The CO functional group is ketone and the aldehyde CHO functional group is aldehyde. But in the case of tertiary alcohol, you may find this COH, that the functional carbon carries no hydrogen. So it can't be able to remove the hydrogen instead it can remove a molecule of water from the adjacent alkyl group to OH. So hydrogen with OH, that is left as water. So here carbon-carbon double bond is developed. So the first two primary and secondary alcohols give rise to the carbonyl compounds on dehydrogenation. But the tertiary alcohol, due to the absence of functional carbon having hydrogen, we are getting alkene as the product since it undergoes dehydration, loss of water molecule. Dehydration of alcohols. Dehydration, removal of water, and this will also follow beta elimination. The OH group of functional carbon having that alpha, and the next to alpha carbon we have beta carbon. So from the beta carbon the hydrogen, and from the alpha carbon the OH getting eliminated. So this reaction can also be referred for beta elimination reaction. And in this case, both the hydrogen as well as OH group of water molecule eliminated from the same molecule of alcohol, and hence this type of dehydration is said to be intramolecular dehydration. Intramolecular means the reaction that takes place within the molecule where the water is being removed. That's why it is called intramolecular dehydration. So primary alcohol, it is actually heated with 443 Kelvin or with concentrated sulfuric acid. Why do we take concentrated sulfuric acid? Once again, it is a dehydrating agent, because the water, if it is formed, may proceed the reaction to the reverse direction, because hydration of alkene will take place to form alcohol. That's why sulfuric acid is here taken, a concentrated one that will absorb the water produced, and hence the alkene will be stable and the reaction will be in the same forward direction. But to the secondary and tertiary alcohol, we do not take concentrated sulfuric acid as well as we do not keep the temperature also. But here in secondary alcohol, we are taking 85% of orthophosphoric acid, such a weak acid. But the temperature is also reduced to 440 Kelvin. There it undergoes alkene. The reaction undergoes to form alkene and water. Similarly, tertiary alcohol, the concentration of orthophosphoric acid is reduced to just 20%. Temperature also reduced to 356 Kelvin. So under this mild condition itself, dehydration takes place. The reason secondary and tertiary alcohol follows E1 mechanism for the formation of carbocation. Secondary and tertiary carbocations are more stable, and hence the reaction condition is reduced. But in the case of primary alcohol, it has to follow the E2 mechanism, because the carbocation is least stable, and hence the reaction condition for primary alcohol is very high. Mechanism of dehydration of alcohol. We can explain the mechanism for primary alcohol as well as tertiary alcohol. Mechanism important. Just like hydration of alkene, dehydration of alcohol also, the mechanism important, we have to learn. See, the primary alcohol that follows E2 mechanism that proceeds in a single step. So the first step is the formation of protonated alcohol. The alcohol, the OH, it has two lone pairs of electron, so that abstract the proton from sulfuric acid. So minus SO3, SO4, H will be removed. So we can write minus HSO4. So here CH2OH with the hydrogen, that forms protonated alcohol. This protonated alcohol, which is highly unstable because the oxygen carries the positive charge, so it withdraws the electron from carbon. Subsequently, the beta carbon from which the proton is eliminated. So the proton minus H plus, and hence we are getting CH2 double bond CH2 and the elimination of water also. So all these steps that take place in a single step because of E2 mechanism. Suppose if you want to explain these 3 steps in stepwise form, you have to say first of all protonation. So protonated alcohol is formed, and the next step actually it removes the water molecule. Subsequently the proton is removed from beta carbon. This is alpha carbon, this is beta carbon. So from the beta carbon subsequent release of proton takes place. But just for knowing, we are writing the elimination of water from the protonated alcohol, it forms primary carbocation. From the primary carbocation, the proton is eliminated, so we are getting alkene with H+. The H+ is the catalyst. So once again, where the H+ abstracted is being regenerated. And tertiary alcohol. Tertiary alcohol follows E1 mechanism and it proceeds with the different step. The first step itself formation of carbocation. But here the carbocation is formed before that the formation of here the carbocation is formed only when protonated alcohol is formed. So in the E1 mechanism of tertiary alcohol, the first step is formation of protonated alcohol. Once again the oxygen atom of alcohol that attract that H+ ion. So we are getting protonated tertiary butyl alcohol. The second step is formation of carbocation, where the oxygen with the positive charge won't be stable, so it withdraws the shared pair of electron from carbon, and hence you are having a tertiary butyl carbocation with water. And following that deprotonation of carbocation takes place. This step is a fast step, but the formation of carbocation is a slow step. So in this is alpha carbon, all the 3 methyl groups are beta carbon. As these 3 methyl groups are identical from either of the alkyl group, you can remove the proton and hence a double bond is developed. So this is what the E1 mechanism of tertiary alcohol. This is E2 mechanism of primary alcohol. Zaitsev rule for elimination reaction. According to Zaitsev rule, the product, the alkene which is formed, the one will be major, where the carbon-carbon double bond should have the maximum number of alkyl substituent. So let us take Zaitsev rule for the dehydration of alcohol. Here we have taken the alcohol 1, 2, 3, 4, 3, 3 dimethyl butane 2 all is taken. So this is a secondary alcohol. This is a secondary alcohol. First step, the formation of protonated alcohol. So this oxygen carrying the lone pair electron abstract the proton. So we are getting protonated alcohol. And moreover, the carbon carrying the functional group is alpha carbon, and this alpha carbon, it has here beta, this is also beta. Zaitsev rule is applied where the carbon having more than one beta carbon. So here also we are finding the molecule, it has 2 beta carbon. So let us have the formation of alkane with the first beta of methyl group, in which once the alcohol protonated, we know it is highly unstable and hence it withdraw the shared pair of electron from carbon. So we are getting the carbocation of this molecule, and subsequently the beta carbon that eliminates its proton, and hence we have the tertiary butyl group followed by CH double bond CH2 minus H+ that takes place. So this is one of the formation of alkene from this given compound. Now let us take this carbocation. That carbocation is designated as 1. In this carbocation you may find the positive charge on secondary carbon. So this secondary carbon that can be shifted to a tertiary carbon of carbocation by doing methyl shift. How methyl shift is possible? This is the positive charged secondary one, and this carbon we said a beta carbon, but it has no hydrogen atom. From the beta carbon only we have to eliminate the hydrogen. Beta carbon, it has no hydrogen, and hence the positive charge is now shifted over to this carbon. Subsequently, the methyl group shifted over to secondary carbon. Now the secondary carbocation is converted into tertiary carbocation. So here you may find the beta carbon. Yes, this is the beta carbon and this is the beta carbon. Once again, tertiary carbocation have two methyl group and both of them will behave like a beta carbon. So let us have the first beta carbon. If I find this is as CH2H, what I will get? This hydrogen, one of the hydrogen from this will be moving towards the tertiary carbon. So we are getting this product. Or if I have this carbon, this is also for me a beta carbon, and I can have this hydrogen that can move towards the tertiary carbon. So I am getting this product. So depends on the different movement of hydrogen from two different beta carbon. This is beta carbon, this is also beta carbon, and the secondary carbocation carrying the hydrogen is also beta carbon. So as it has 3 beta carbon, out of which 2 of them are similar methyl group, the other one is CH. So from the methyl group, when hydrogen is eliminated, we will get, this is the alkene produced. Or the adjacent beta carbon from which the hydrogen is eliminated, and this is what the alkene we are getting. When you compare the formulas of alkene, so let us designate the product formed will be ABC, where A is the doubly bonded carbon, one it has a tertiary butyl group, the other has no alkyl group. In B, the doubly bonded carbon, one of them has no alkyl substituent, but the other it has one methyl and one secondary propyl. In the C, you may find both of the doubly bonded carbon have 2 methyl substituent. So you, according to Zaitsev rule, this is doubly bonded carbon with more number of alkyl substituent. It becomes major and it is about 64% formed. Here Zaitsev rule is partly satisfied with one of the doubly bonded carbon. Here it is about to form 33%. In this case, it has only one alkyl substituent, it is formed only 3%, out of which the 64% of alkene is found to be a major, the other 2 products are minor. The last property of alcohol, Swen oxidation. It is said to be a name reaction because in this oxidation some specific reagents taken for oxidation. Usually oxidizing agents we have. Besides those oxidizing agent, Swen, he preferred these 3 mixture of compounds for the oxidation of alcohol. The mixture of compound that contains dimethyl sulfoxide, DMSO, dimethyl sulfur with oxygen, so the name is dimethyl sulfoxide, and oxalyl chloride along with triethyl amine, it is a tertiary amine. So when these mixtures taken for the oxidation of alcohol, then the reaction is said to be Swen oxidation. Here the alcohols are oxidized to carbonyl compounds only. So we have taken the secondary alcohol 2-propanol. It is oxidized to propanone. The ketone is formed because of secondary alcoholic group. We are getting ketone upon oxidation. And these reagents, they are converted into DMSO into dimethyl sulfide, and in the oxalyl chloride, 1 carbon monoxide is removed, and this carbon monoxide with this dimethyl sulfoxide that gets removed as carbon dioxide. Out of the 2 chlorine atom, the 2 hydrogen of CHOH gets removed as 2HCl. So in Swen oxidation, the oxidizing agents are totally different. That is the mixture of dimethyl sulfoxide, oxalyl chloride and triethyl amine. When this used for the oxidation of alcohol, we will get their respective carbonyl compounds. That's all the properties of alcohol. The next let us see the properties of phenols. The chemical properties of phenol. Already I told you the phenol, it has two types of reactions. One due to the presence of OH group, the other one due to the presence of benzene ring. So let us find first of all the reactions due to the OH group of phenol. The presence of phenol that can react with metal or base or esterification, or it may undergo oxidation reduction reactions. So with the metals, phenol, just like alcohol, the metal displaces hydrogen atom of phenol and hence we are getting sodium phenoxide. Why these hydrogen atoms are displaced? This is because the acidic nature of alcohol and phenol. Let us discuss about that acidic nature after this session. So here the hydrogen is being displaced. So we are getting sodium phenoxide. This is a bulky base group. With the strong base, not only with the metallic sodium, phenol can also react with the strong base. This is because phenol is a weak acid and hence it reacts with base to form the same sodium phenoxide and water. The water is this OH and H of the group will be removed. So we are getting sodium phenoxide. But alcohols do not react with bases. That can react only with metal. They do not react with bases because alcohols are much weaker acid than phenol. That's why alcohol do not react with bases. Next reaction, esterification. Just like alcohols, phenols also undergo esterification. So if C6H5OH with acetic acid, or you can say it is ethanoic acid. When phenol reacts with ethanoic acid in presence of concentrated sulfuric acid, we will get phenyl acetate and the water will be absorbed by concentrated sulfuric acid. So the reaction, reverse reaction will be prevented. Suppose the same esterification, if at all, carries out with acid halide, then the reaction is said to be Schotten-Baumann reaction. It is a name reaction. So here the phenol that may react with either ethanoyl chloride or its common name is acetyl chloride or even benzoyl chloride. C6H5COCl is called benzoyl chloride. CH3COCl is called acetyl chloride. So when phenol reacts with the acid halides in presence of base, they do form the same ester of phenyl acetate. Here, why do we take the pyridine, a base? Pyridine is a base because this base, it neutralizes the acid produced in the reaction and hence the formation of the ester will be stable. So, phenol with the acid halide is known as Schotten-Baumann reaction. And how do you convert phenol into benzene? That is possible by distilling with zinc metal, where zinc metal that removes with the oxygen to form zinc oxide. So phenol is converted into benzene. This is one of the conversion you may consider. So phenol, it is converted into benzene when phenol distilled with zinc metal. Very important question too. Then with ammonia. Ammonia, in presence of anhydrous zinc chloride, a water molecule will be removed from ammonia, one of the hydrogen from ammonia with OH, that is left as water. So phenol is converted into here aniline and the produced water will be absorbed by anhydrous zinc chloride. Then oxidation. Alcohol oxidizes to their carbonyl compounds, aldehyde or ketone, but phenol that oxidizes to 1,4 dione. So this is also called benzoquinone. The name of the compound is benzoquinone. So when phenol oxidized by acidified potassium dichromate, it gives benzoquinone, or you can say benzene 1,4 dione. That is also its name. And reduction. The benzene ring is converted into cyclohexane. So how it is possible? When phenol is heated with nickel hydrogen at 160 degrees Celsius, the C6H5OH is converted into C6H11OH. So it requires 3 molecules of hydrogen to convert, and hence we are getting cyclohexanol. So phenol can be converted into cyclohexanol by the reduction process. That's all the reactions in which the OH group involved in chemical property of phenol. The next properties of phenol is the reactions due to benzene ring. So in phenol we have the OH group as the functional group. The oxygen atom of OH group has 2 lone pair electron. This lone pair electron is in conjugation with the benzene ring, and hence the molecule where it gets resonance hybridized. So we are getting the conjugation structures of phenol. So here when the lone pair electron moves towards the ring, the valency of carbon goes 5, and hence the pi electron comes out of it and occupies the second position. And in its further resonance hybrids, this negative charge enter into the ring, and this pi bond it comes into the 4th position. Later on, this negative charge goes into the carbon, and this one goes to 6th position. So we may find the presence of negative charges at 2nd position, 4th position as well as the 6th position. So the formation of negative charges and 2, 4, 6 position that decides OH is ortho-para directing group. And this OH group highly activates the benzene ring towards the electrophilic substitution reaction, and hence the reactions of phenol, it doesn't require any vigorous condition that can take place even under mild conditions. But in haloarenes, the halogen deactivate the benzene ring, so we had taken the catalyst under vigorous conditions and all. But here the OH group activate the benzene ring, so because of that the benzene that can make that incoming electrophile to ionize themselves, and hence they do not require any strong reaction conditions. Let us see first of all halogenation of phenol. Phenol that can undergo halogenation in 2 different ways. One with the bromine in carbon tetrachloride, and the other the bromine in water. Bromine in carbon tetrachloride, the carbon tetrachloride is a non-polar solvent. Under this condition, phenol can give orthobromophenol or parabromophenol. The orthobromophenol is usually a minor product, but the parabromophenol that goes major product. But in the case of bromine water, phenol gives polysubstituted compound, say 2,4,6 tribromophenol, that makes a white precipitate, and hence the reaction of phenol with the bromine water is treated as test for phenol. So the given compound, whether it is phenol or other, can be identified by using bromine water. The next reaction, nitration. Nitration also possible with the concentrated nitric acid and dilute nitric acid. With the concentrated nitric acid, phenol gives once again polysubstituted phenol. So we have the nitro group at 2nd position, 4th position and 6th position. So this is known as 2,4,6 trinitrophenol, or it is commercially known as picric acid. But in the case of dilute nitric acid, just like halogenation, it forms orthonitrophenol and paranitrophenol, where paranitrophenol is found to be a major product while orthonitrophenol is a minor product. At the same time, the mixture of these two nitrophenols can be separated by the process of steam distillation. Why that process is specifically taken? Because this orthonitrophenol is steam volatile. That means it can vaporize at the temperature of steam. So it is said to be steam volatile. Why this compound particularly steam volatile compared to paranitrophenol? This is because this orthonitrophenol, it has intramolecular hydrogen bonding. So OH of the hydrogen and oxygen of NO2 group that makes a hydrogen bond within the molecule. That's why it is said to be intramolecular hydrogen bonding. This intramolecular hydrogen bonding is weak compared to intermolecular hydrogen bonding. That's why paranitrophenol has higher boiling point compared to orthonitrophenol. In paranitrophenol, we may find the hydrogen bond exists between the molecules, but here within the molecule. So such type of hydrogen bonding is said to be intermolecular hydrogen bonding, and hence it has high boiling point compared to orthonitrophenol. The another reaction of electrophilic substitution in phenol is nitrosization. Nitrosization is nothing but addition of nitrosyl group to the phenol. So here when nitrous acid is treated with the phenol, that forms para-nitrosophenol. So the para hydrogen with the OH, that is left as water. So we are getting para-nitrosophenol. Then the next reaction is sulfonation. Sulfonation is carried out with the concentrated sulfuric acid at 280 Kelvin, that can give rise to either ortho or para hydroxy benzene sulfonic acid. So ortho, these two OH group may removed as water, or para, these two OH will be removed as water. So by the loss of water molecule, we get ortho-hydroxy benzene sulfonic acid and para-hydroxy benzene sulfonic acid. So in which the para isomer is major and the ortho isomer is minor. The next reaction is coupling reaction. So in coupling reaction, we will get a dye, the coloring matter. Actually, coupling reaction is proceeded with diazonium chloride and phenol. So diazonium chloride, we know C6H5N2Cl. When it is treated with the phenol, the hydrogen atom of opposite to the OH group, say the para position, that hydrogen, it combines with the halogen of diazonium chloride, hence it gives rise to para hydroxy azo. This nitro, N double bond N is said to be azo. Para hydroxy azo benzene is formed. This is the color of the compound is a red orange dye. So from the formation of this colored dye, this test that can be taken for test for phenol. The next one, Thalian reaction. By this reaction, you can able to prepare a synthetic indicator known as phenolphthalein. This is used as indicator for acid-base neutralization reactions. How it is prepared? It is prepared from phthalic anhydride and phenol. Phthalic anhydride, once again the 2-carboxylic acid. Phthalic acid formula is 1,2-benzene 1,2 dicarboxylic acid. This is phthalic acid, from which a molecule of water, when it is removed on heating, it forms phthalic anhydride. This phthalic anhydride on reaction with the phenol in presence of sulfuric acid that removes a molecule of water such a way one of the CO group with the 2 hydrogen atoms of 2 phenyl group that makes water, and hence the carbon double bond that links with the 2 of the benzene ring, we are getting phenolphthalein. This is the structure of phenolphthalein. And one more information, in coupling reaction we had taken sodium hydroxide, a base. Why the base is used? Because the formation of HCl has to be neutralized, that's why we are taking base for the coupling reaction. And the next one, Riemann-Tiemann reaction. In this reaction, phenol is converted into salicylaldehyde. So in Riemann-Tiemann reaction, we can prepare a hydroxybenzaldehyde, that is called salicylaldehyde. How it is prepared? When phenol treated with chloroform and sodium hydroxide. The reagents only determine what name reaction that follows, and what is converted into what, that also informed by the name reaction. So here the chloroform and sodium hydroxide is used for the conversion of phenol to salicylaldehyde. When it is taken, the base that alters the OH group into the salt of phenol, and the hydrogen atom of this ortho position that can combine with one of the chlorine atom. So here we will get minus HCl. Here we are getting minus HCl. In the place of hydrogen, the CHCl2 group is formed, where we are getting gem dihalide. Upon the treatment with the sodium hydroxide, both of the halogen with the sodium is removed as minus 2 NaCl, and hence the gem diol is formed. Gem dihalide is into now gem diol. Gem dihalide is stable, but gem diol is not stable because of the bulky nature of OH group attached to the same carbon atom, and hence a molecule of water is removed from the group, so that is converted into aldehyde, and this followed by acid hydrolysis we are getting salicylaldehyde. The next one, Kolb's reaction. Kolb's reaction converts phenol into salicylic acid. The above one is salicylaldehyde, where we prepared hydroxybenzaldehyde. The salicylic acid is hydroxybenzoic acid. How it is prepared? Once again the reagent. First of all, phenol is converted into sodium phenoxide by the loss of water molecule minus H2O. So we are getting sodium phenoxide, to which the carbon dioxide just adding at the temperature of 400 Kelvin and 4 to 7 atmospheric pressure. How the reaction proceeds? See, this has the ortho hydrogen that can be attracted by the oxygen atom of ONA. Subsequently, the double bond of carbon dioxide attacks that Na plus, and this makes the electron carbon plus that attacks this nucleophilic site, and hence we are getting sodium salt of salicylic acid, or you can say sodium salicylate. Upon acid hydrolysis, this NaCl will be removed, so we are getting salicylic acid. So in Kolb's reaction, phenol is converted into salicylic acid, that is a hydroxybenzoic acid. Next one, how this salicylic acid undergoes esterification. Salicylic acid, it has both OH and COOH. Esterification is possible one alcohol with one acid, or one acid with one alcohol. In this salicylic acid, you have both acid as well as the alcohol. So it depends on where the reaction to take place. Whether alcohol, you have to take the acid derivative, or if you want to take the reaction at carboxylic acid, then the reagent, the incoming group must be an alcohol. So here we are going to prepare aspirin. Aspirin is the medicine which is used as analgesic and antipyretic. Analgesic means the pain reliever or pain killer. Antipyretic, that is for reducing the fever. So aspirin, it has the dual property of pain relief as well as used to reduce the fever. So this is prepared by treating salicylic acid with acetic anhydride. This acetic anhydride, it is an acid derivative, so the reaction will take place in alcohol. So you can combine, this is the group as CH3COOH, that is removed. So oxygen with the COCH3, we are getting acetyl salicylic acid, that is known as aspirin. Okay students, let us close our today's session. Today we have discussed about the preparation of phenol and physical and chemical properties of alcohols and phenols. So let us continue this same chapter in our next session. Until then, bye bye.